Hi friends, welcome to the tutorial of theories of failure. Failure theories predict under what load condition your material of design fail. And good understanding of these theories are very important in design of civil structures or mechanical equipment so that your design won't fail. Let's start. Before going to the main topic, a small analogy which is related to theories of failure. Consider this weightlifter. Assume 50 kg is the maximum lifting ability he has got. Means he won't be able to lift more than 50 kgs. That is his maximum capability. If I add one more kg to his weight, he will fail to lift it. Now consider the same weightlifter in a different scenario. That is this. He is again lifting 50 kgs here, but in different fashion. 15 kgs on one hand, 25 kgs on another hand, and 10 kgs on his head. So in first scenario we know 50 kg is the maximum lifting ability of this lifter. So is it true to say in second case also he won't be able to lift more than 50 kgs? It's not exactly true, right? But it is pretty okay, a pretty good assumption. So if you can assume so, this will be known as a theory of failure for a weightlifter. So what we have done just now, we had a simple loading for a weightlifter and we found a maximum limit for the weightlifter. And in second case we had a complicated or complex loading for the same weightlifter, and we assumed that the first simple loading case is applicable for the second complex loading case also. So this is all about theories of failure. In material failure also we will proceed in same fashion. So we will go across it. Here it is. So I have got two cases here. First is a simple loading case, second is a complex loading case. So you can well understand, first case is a simple tension test case that you perform in laboratory and results are well available. And just like the weightlifter case, here also you know at what load condition my material will fail under simple tension test. And using this data you will be able to predict under complex loading condition also how my material will fail. So this is the way we are doing it. From simple tension test we know what's the maximum stress a material can withstand, or what's the maximum strain it can withstand, or what's the energy stored during the failure. Using this data you will predict under complex loading condition when the material will fail. What you will do, you will just compare these two values. You will say when maximum stress of my complex case exceeds the maximum stress of simple tension test, my material will fail. So similarly you will do for other variables also. So that's the concept of failure theory. But before proceeding to the failure theory, it's better to understand two concepts in a better way. First is about simple tension test. We'll go across it in more detailed way. Second, I told we'll compare maximum stress or maximum strain in a complex loading case. So in order to find this maximum stress or maximum strain in a complex situation, you have to understand something called principal stress or principal plane. So we will go across this also. So after covering these two topics, we will see what are failure theories. So first, a simple tension test. Here it is. And here you are pulling the rod with a tensile force and it will keep on extending and it will have different characteristics as it goes on extending. Up to Hooke's limit, strain induced will be directly proportional to the stress, and up to elastic limit the stretch will be elastic, means if you release the load from this point it will regain its original shape. But after elastic point, even if you release the force, it won't get its original shape. It will undergo permanent deformation. So it's like a damage to the material. So you can well assume that elastic limit is the failure limit. After that you can assume that your material has failed. But this elastic limit is little bit difficult to measure during a simple test. But just above elastic limits there is one more limit called upper yield point, where yielding or fast deformation of material happens. And this point is easy to measure. So you will assume that yield point is the failure criterion, or at yield stress failure of my material happens in simple tension test. This is what material will look like at the time of yielding for a ductile material. It will form a neck and there will be a shape deformation to it. Now we will have more analysis on simple tension test. Here it is. So assume your material has reached the yield limit, it is under yielding, so force you applied is equivalent for that. Now what is the maximum normal stress induced at the time of yielding. It's very simple. This will be same as yield stress, because yield stress also is normal in direction. So maximum normal stress is same as yield stress. And what's the maximum normal strain at the time of yielding? Maximum normal stress divided by Young's modulus, you will get maximum normal strain. Here it is. And what's the total strain energy stored at the time of yielding? Strain energy is area under stress strain curve, so you can well formulate it like this. And now, what's the maximum shear stress at the time of yielding? And maximum shear stress happens at an angle 45 degree with horizontal like this at this location. And here is a force diagram of that. And please note that area of cross section at 45 degree angle is A root 2. You can do a simple force balance of this diagram, and you can prove that shear stress at 45 degree or shear stress maximum is same as half of yield stress. The last parameter, shear strain energy stored at the time of yielding. This will be given like this equation, where G is shear modulus. Now you have got 5 parameters. In a failure theory, what I do, I will take any of this parameter and I will compare with the maximum value obtained in an actual system, and I will say if in my actual system any of this value exceeds, my material fails. Here you have 5 parameters, so you can formulate 5 failure theories. The next thing to understand, the concept of principal stress and principal plane. It comes like this. This is an actual system under complex loading condition, and I want to find out at the red point, which is inside the material, what's the maximum normal stress induced there. Or in a simple figure, it will be like this. And you know, there can be infinite number of planes passing through this point. So on different planes there will be different normal stresses. But at one particular plane there will be maximum stress induced, and this plane will be known as principal plane, and stress on this plane will be known as principal stress. And if you want to find out these values, means orientation of the plane and value of stress, you have to do Mohr circle analysis, where you will give force as your input and you will get principal stresses and principal plane as output. And for a 3-dimensional system, there will be 3 principal stresses when you do Mohr circle analysis. And similarly, there will be 3 planes also, like this is plane number 1, plane number 2 and plane number 3. And if you want to know maximum stress, normal stress value of at this point, just compare this sigma 1, sigma 2, sigma 3, and maximum of that will be maximum normal stress at that point. And a funny thing, and minimum of these 3 value will be minimum normal stress at that point. And one thing to remember, on all these 3 principal planes, shear stress values will be 0. Now we understood what's the value of maximum normal stress at a given point. And what about maximum shear stress value? That will be given by simple equation like this. Usually we denote sigma 1 for maximum normal stress and sigma 3 for minimum normal stress. So just find out difference between these 2 values and divide by 2. That will be maximum shear stress induced at that point. Now let's go across failure theories. And as I said earlier, there are 5 failure theories. And the funny thing is, just by looking at name of the theory, you will be able to formulate the equation of failure or the condition of failure. Here, name of the failure theory is maximum principal stress theory. So as the name suggests, my material under actual load condition will fail when maximum principal stress induced in material is same as maximum principal stress induced in simple tension test. So maximum principal stress in actual case is sigma 1, we got from Mohr circle analysis, and maximum principal stress at simple tension test is sigma y. So just compare this, and this is the condition. Under this condition, according to this theory, my material will fail. And experience has proved that this theory is good for brittle materials like glass, crystal or ceramics, but not for ductile material. If you are working with ductile material, please avoid this. Next theory, maximum shear stress theory. As name suggests, it says that my material will fail when maximum shear stress induced in my material is same as maximum shear stress induced in simple tension test. And you know maximum shear stress in actual system is half of sigma 1 minus sigma 3, and maximum shear stress at simple tension test is half of field stress. So just equate these values and this will be the condition of failure. And this theory holds good for ductile materials such as steel and aluminium, and it is a pretty good theory to work with. Now the third theory, maximum principal strain theory. So you can assume that when maximum principal strain in my actual system is same as maximum principal strain in a simple tension test, the material will fail. Maximum principal strain in actual system is like this, where mu is Poisson's ratio just to consider the effect of lateral deformation, and maximum principal strain in simple tension test is sigma y by Young's modulus. So this is the condition for that. This theory doesn't work for any material, and if you use this theory for some design purpose, you might end up in a wrong design, a disaster. So better to avoid this theory. Now the fourth theory, total strain energy theory. Here again, when total strain energy in an actual system is same as total strain energy in a simple tension test, the material fails. And total strain energy can be represented like this, a pretty complicated equation in terms of principal stresses. And you know total strain energy in a simple tension test is sigma y square by 2e. So equate these quantities and this is the condition for failure. And again this theory works well for ductile materials. If material used for design purpose is ductile in nature, you could use this theory as a design criterion. Now the last and fifth theory, shear strain energy theory. So here again, as the name suggests, we are comparing shear strain energy in an actual system to shear strain energy in simple tension test. Here it is. This is for actual system and this is for simple tension test. And regarding this theory is considered to be the best of 5 by the industry, and it works well for most of the cases. If you are into some serious design of civil structure or mechanical equipment, you could use this theory for design of them. And this theory is also known as von Mises theory. And we will introduce one new parameter in this theory like this, something called von Mises stress. It is defined like this. So if we can define von Mises stress as the parameter given, then your failure condition will be reduced to such a simple equation. You will say when von Mises stress of actual system reaches yield stress at simple tension test, my material fails. So as a conclusion, this theory is the most valuable theory of 5 theory, best for design purpose, especially when you are dealing with ductile materials. Thank you for watching the video. Hope you got a good introduction to theories of failure. And if you are in www.learnengineering.org, you can check more industrial applications of these theories.